where, okay, and it's very hard to spot where these errors live. We can't say, okay, this case we would have error definitely, and that's we should deal with it somehow. Rather, we would have a lot of outputs like this slope, and this slope has actually a lot of inaccuracies, and that's a term for it now, hallucinations. Okay, the only option we have is to learn how to deal with it, how to establish uncertainty, and how to estimate it, and after that, how to improve decisions using our uncertainty estimates. So in my talk, I would focus on these different uncertainty estimates, hallucination detectors, and also about how we can use these estimates in the applications. Like, can we improve RAG, or can we improve decision making in general, on and on and on. And also in the first part, I would look not about like general approaches, general heuristic methods, but I will try to connect it to a pretty nice emerging area in LLMs, specifically mechanistic interpretability, because, okay, we have this black box, okay, not a black box at this slide, it is green box, but anyway, it's something that does a lot of tasks inside, like reasoning, like attentions, and other layers, and on and on and on. And we try to understand this, and if we somehow can understand what is going on inside, we can try it to improve the decisions, and specifically we can try to estimate uncertainty. So basically many methods that we consider today for estimate uncertainty for large language models would be about how can we, for this uncertainty, to produce this estimate inside LLM or with little additional cost, and we will discuss what other scenarios are possible. Some of them were also discussed by Artem and other people, but anyway, I hope that I can provide some additional perspective, or maybe kind of in some case, okay, we are learning something, so repetition is, I suppose, not that bad. So about uncertainty estimation, why we should care about it. Like, let's start with two applications that can help us to make better decisions based on uncertainty. One thing in medicine, we typically want our decisions to be very confident, and we don't want to make errors. And one example come even not from LLM world, but rather like even for images. Like we have images like this, and we want, it's about blood samples and some reaction of blood sample to some specific thing. And we want to find out, did the reaction occur or not. And sometimes it did not occur because the blood sample itself is bad. For example, it is too small amount of blood taken. And because of this, we have a high uncertainty about this result. And because of this, we should retake this test. And based on the uncertainty of this model, we can make a simple decision to retake it. And because of this, improve overall pipeline. Another scenario when you typically need uncertainty is active learning. In this case, we typically say that we don't start the story from uncertainty, but rather we would say that we have limited budget to label our samples. If the number of samples we can label is limited, and the total number of samples is very big, then we have a problem on selecting good items to label. Like, for example, we have texts, and we can read only like 10% of the texts. And we want to make something good about this. So what we can do, how can we approach the problem of labeling only like selected specific number of texts? One way to do this is to say, let's just pick some random sample of this text and hope for the best. Definitely maybe not that bad strategy actually, and it works pretty well. But we can imagine many cases where we can improve this. For example, we label these texts to later train a model. So basically, we need texts that are good for learning this model. And some texts definitely are better than the others. Let's consider not text, but a simple two-dimensional example. So we have two features, like feature 1, feature 2, and we have two class classification problem, like blue points and red points. And we somehow want to produce a decision boundary between these two set of points. And I would say that labeling point here or here, it doesn't approve our decision, our model too much, because we already know that this region is something blue and this region is something red. So what really is for interest for us is something in the middle, in between red and blue point, because if you know that these points are blue, then the decision would be like this, decision boundary. If we know that they are red, it would be rather like this. So basically, if we kind of make some algorithm to select points for labeling, it can improve the overall decision process, overall model in the end. And natural idea to deal with it is to obtain uncertainty for each point. If you know that the model is very uncertain about its decision here, then we should label this point in the first place. So basically, uncertainty is a good proxy for the selection of points problem. And it happens not only in this two-dimensional example. It happens like in Bayesian optimization and similar problems. And it happens in active learning for LLMs as well, like for something like few-shot learning, when you select examples to look closely at by experts and then provide these examples to an LLM to make better decisions. Also, there is a usual story that uncertainty types, there is more than one uncertainty type, and typical decomposition considers data uncertainty and model uncertainty. We heard about this, I don't know, like 10 times this school, but okay. So I include some images so you can now look at what this data uncertainty is for, again, some pretty simple problems. So imagine that you have two class classification, like blue cycles, dogs, and red triangles, cats. And in some cases, we can have high data uncertainty. It means that we have a naturally genuine, complex example to classify. Something between cat and dogs. This cat dog, you look at this guy here, like at the end of green arrow, and you can decide, is this a cat, is this a dog? Because actually it's not about the model, it's about the example itself that's too complex. Another kind of natural example for high data uncertainty can be something very blurry. For example, you recognize faces, and for this face recognition, we have, for example, we take these photos in the night. And because of this, the lighting is bad, and we can make confident decisions. For LLM, data uncertainty can be somehow related to the complexity of the problem. If you have some very complex mathematical problem, we can say that we have little chances to solve it because it's already very hard to solve. Another type is model uncertainty. In this case, we typically refer to the cases where we don't see, to the regions where we have not seen examples in our training data. For example, here again we have usual cat and dogs, and we have this specific cat and dogs like somewhere that we have never seen before, and the model does not know about these examples, and maybe because it does not know, we can help the model by including more examples, learning it, and reducing this uncertainty. For LLMs, it also can be the case because actually many advocate that LLMs are very good for many problems, but actually if you go slightly beyond the in-domain data, it leads to pretty unconfident and often pretty crazy decisions, and it does not look right. I mean, for example, if you want to write some CUDA kernel for kind of improvement of the speed for matrix multiplication, but these matrix sizes are not typical, then you will get something like pretty bad on average. If you want to draw something, I don't know, for example, you can prompt ChatGPT to draw an ASCII to cat, and the result would be far worse than you would expect. So again, these uncertainty types are often related to different types of problems, to different types we want to solve. For example, if we are talking about medical diagnosis, typically what we focus is data uncertainty. We believe that we collected all the data we can see, and the problem can be with the quality of a sample. If you're talking about active learning, typically data uncertainty is not should we look at, because data uncertainty we can't reduce. It does not matter how much data we have. In the end, we will have this data uncertainty. But for model uncertainty, that is the thing we can reduce. We can collect more data in these regions we care about and improve the overall decisions. And the same story happens in LLMs as well. Okay, there is an example of hallucination. Okay, a person asking about something mushroom, and LLM gives very dangerous answer about this. Okay, just eat it, it's very good. And actually there we also can refer to different types of uncertainty, different types of hallucinations. It can be related to that, okay, either has one request, but the answer is about something different, okay, about not dinner but lunch. It can be about that it ignores context. It can be about facts. So we know that some facts become outdated, or some facts are as a tail of the distribution of the facts, and because of this, we would have not very rich training data used to train this specific part, specific facts, and the model, as a result, can produce something good. And so I would say that there is a lot of papers on hallucination detection, on explanation of hallucinations, and all other stuff related to this area. In this case, we would largely focus on faithfulness hallucination detection. It means that we try to find out how truthful is the answer related to the context. So it's about this input conflicting hallucinations. Because typically, we have not only a query from a user, but as well some context, like it's a run scenario. So we start with search of some relevant documents, we include them, and in the end, we can end up conflicting with this input. It means the faithfulness hallucination. Also, we will briefly consider what are the benchmarks for hallucination evaluation. It is kind of relevant to the questions from some of you, what is a hallucination? And really, it's very important, a very good question. Not many answers, unfortunately, that are 100% accurate, I suppose. No single answer at all. Also, we'll try to look slightly at what we can do to mitigate hallucinations with fine-tuning, and how we can use uncertainty to improving, mitigating, to making it more efficient. Okay, so we start with a pretty simple baseline that you, again, I suppose, heard a couple of times. If you are talking about an LLM, we have the token production process. We generate tokens one by one, and when we generate a token, we select with some probability, or with the highest probability, some token. So M is our dictionary size. We have probabilities for each token to be generated, and we can say that our certainty is this maximum of this vector of probabilities. For example, if the LLM is very confident that the next word is times, like with probability 1, and okay, it often is the case. Often we see in LLM that it is very confident. It's very confident about most of the tokens. It just generates the next token, and the probability for it is about 1, so we're very confident. For some tokens, it's not like this. Okay, we can have synonyms, for example, or we can have overall kind of complex problems, or like lack of knowledge, and so model isn't certain about this output, and we can say that uncertainty is 1 minus certainty, and specifically 1 minus the maximum of all these probabilities. Actually, when we refer to this type of uncertainty, we can say that it is about the probability of an error when generating a specific token. It is also not very robust, because we're taking the maximum, and maximum kind of is not very robust function. So because of this and some other reasons, many people instead are using entropy of the distribution, like on how non-uniform this distribution is. And given this entropy or given a certain estimation, we can say that this is our uncertainty. For classification problem, when we have kind of some classes instead of a dictionary, we have, for example, 10 classes, it works pretty well. But anyway, we can try to improve this because as we see in applied problems, there is some difference between what this entropy or max prop measures and what we actually want. For example, we can try to fine-tune the specific head that produces this uncertain estimation and get a better uncertain estimate with respect to like most of the metrics. Actually, kind of here we need to do some tricks, like regularization of the base model for this head we train, and kind of we want to be not that far away from the original parameters for this head and so on. But overall, it means that these measures like entropy, like maximum probability, they are not perfect. They lack some understanding of uncertainties. For example, they are not very well adjusted to out of distribution sinks. And there are kind of many other methods that can improve over this. For example, if you consider kind of Hallow-based distance between embeddings, if we have a new object and we measure the distance between this embedding of the new object and the objects already presented in the training sample, typically we see that this is a pretty good thing to measure the uncertainty. And this entropy or max prop, they are not good in this case. They kind of still will produce something pretty regular. So it means that we have, again, many ways to measure uncertainty, and we should tailor it to specific problem we are solving. Another example is that even in this pretty natural ensemble way to think about uncertainty, so we sample this theta case from some big model, like, we use kind of Monte Carlo dropout to produce an ensemble of classifiers and LLMs. We measure the average confidence, so we measure the entropy of this guy. Then it can be easily improved with weights of objects in this ensemble. So it means that we try to adjust the distribution of the original posterior distribution to the distribution we produced with this theta case, because often they are not something that we want. For example, typically a story to produce another member of an ensemble, if you're considering a convolutional neural network, is just to say, let's run the optimization of the parameters, but change the random seed, the initialization of the parameters of the model. When we are doing this, we end up in some local maximum, and actually it should not reflect the true posterior distribution. And because of this, we can do some improvement. And one example of doing this is use kind of comparison of embeddings produced by different models. Specifically here we use kind of topological data analysis embedding, kind of because it's very hard. Another pretty hard problem how to compare two different spaces of embeddings, because it needs to be invariant to rotation, to shifts, and so on. But anyway, it's pretty easy to work in the end and pretty lightweight. Now let's move from kind of uncertainty to hallucination detection. And I would say that I want to answer 3 questions, and I hope this question also of some interest to you. The first question is about can we detect hallucinations? We always say, we have these hallucinations, but what if these models are kind of even more smart, even smarter than us? Would it mean that we are trying to solve some ill-posed problem? Also, the second question would be about, we know that, we have the answer to the first question, and you will know it soon. The second question is, can we judge about certainty and uncertainty of a model about its internal states? So if this answer is positive, it means that we have a fundamental flaw in our LLMs, as some fundamental results of what we are talking about. It means that these models are trained in a way that they try to answer confidently, even in the actual internal reasoning, they are not confident at all. And the third question is how can we join our efforts from mechanistic interpretability and from uncertainty estimation to improve hallucination detection for LLMs. So let's start with the first question. Okay, you already know what is hallucination detection, so let's go to the next slide and say that we can pretty easily produce some hallucination detectors. You need to get some sampled answers, kind of. You increase the temperature from 0, you produce n answers, and you compute how close these answers to the original text produced by an LLM. And here we can, for example, use an LI model that basically says how similar these two texts are with some very natural score. We aggregate this comparison between the original text and all the send samples to obtain SelfCheckGPT score. It is a pretty good score, but the main problem of it is, okay, in a way you can say, okay, something similar to ensemble. Yes, we have kind of some internal ensemble, especially for long text, and this kind of like this. But we inherit the problem with typical ensemble. It's an expensive method. For example, okay, in the original paper, the number of generations, additional generation, is 20. It means that we increased the inference type for this model 20 times just to reduce the amount of hallucinations. Typically in production, that is something we can do. So again, we can try to improve this with semantic uncertainty, like by grouping some outputs to remove the semantic part of uncertainty and to make kind of more reliable entropy estimation that kind of better reflects that we are hallucination. But overall, the problem remains. Even in this paper, kind of published in Nature, by the way, we have this problem with high amount of computations to produce things. So we can try it. Okay, we have the positive answer to the first question. Yes, we can detect hallucinations in a pretty simple way, and you can know that this guy is even black box, because we don't need to know what's internally. We just query the IP, we have all these responses, comparison with another model, and so it is a black box method. This guy is white box, because we need these probabilities inside. But anyway, we know that model, okay, that we can detect hallucinations, and actually, if you look at the scores, they are pretty high, especially if you don't have like domain transfer inside it. The second question I was asking is about, can we say something using only internal states of a model? And the answer is also yes. Okay, and I'm not sure if it is the first paper, but it is one of the first papers that we're exploring this question. They just do the simple thing. Let us select some layer in a neural network in our LLM. At this layer, we have embedding of our text. We can do something like min pooling of this embedding to have a single vector here. And this single vector can be used to do so-called probing. So to train a logistic regression in supervised way to predict the probability of hallucination. So basically, we solve a two-class classification problem with our representation vector being some aggregation of embeddings of tokens at some layer. And actually, when we do kind of different type of questions, when we train this model, the score is pretty good. Accuracy can reach, I don't know, up to 0.8 for this supple approach. So it means that internally we know this. And what is also interesting is that when we are doing probing on different layers, we can try to select the best layer. And the best layer is typically not the last layer in the model. Maybe you can think about it like this. But rather something in the middle. So it means that the model kind of reasons and understands better that it's uncertain in the middle. And after that, it tries to kind of cover this answer with some certainty, with some kind of some confident words. Also, one important thing to explore here, one important tool to look inside what LLM is doing is attention metrics. So attention metrics, okay, yes, attention metrics is, I hope all of you know to some extent what is attention metrics. Okay. At least it would be very strange if you don't, but okay, very quick reminder. So basically we have some tokens generated. We have some tokens or tokens like in the context, specifically to the question, and it is beginning of the sequence. And we have some tokens in the answer. And we have at each layer attention metrics, like it is lower diagonal because we generate tokens one by one. And this matrix describes what tokens have been used to generate this. For example, for generating like it, we mostly refer to it and also to something else like capital. For Paris also we have kind of some attention pattern on how we were connected to the previous tokens. And so we have this matrix, and actually it's a natural idea to analyze how this matrix can help us to understand what is hallucination and what is not hallucination. And one way to do this, like pretty again, okay, if you are kind of splitting it to different steps, all ideas look very natural, but actually this we present the ideas that work, and there are many other ideas, okay, that can be constructed in a similar fashion that does not work. So what we are doing? We have some token in the end. For example, this is our paree, and we have all previous tokens, and we have tokens like for the prompt and token for the response, all the previous tokens. And we can calculate the attention to the tokens in the prompt and to the token in the response. And we compute the ratio, the attention in the prompt divided by the attention to the prompt plus the attention in the response. And it means how much this specific model is looking into the prompt when generating a specific token. So we can generate this look-back ratio scores for all layers, for all heads, and aggregate them in a big vector. And it would also form a base for our prop. So it would be a vector, on top of it we train a logistic regression. Okay, in this case it's kind of a linear classifier, and it produces the probability of hallucination. So also supervised method, but we use in a way better features. And actually what is important in many of these applications is how many features we should consider. Because basically this guy kind of, if we don't select specific layer and specific head, it has a lot of features. We take features for all the layers, for all the heads, kind of about 1,000 heads in kind of even medium size like 7B models. And it means that actual dimensionality of this vector, if you can concatenate all these embeddings at all these things. And okay, we don't talking even about kind of specific parts of that relate to specific tokens, but as we aggregate everything, so we have, okay, 1,000 times about 1,000, we have 1,000,000 features for our classification problem. So if we even want to train logistic regression, maybe some regularization, it means that we need about 1,000,000 samples, 1,000,000 labeled samples to make it work. So we need a train sample like this. For sure, for regularization, it can work better. But overall, it means that feature selection can be crucial, because in reality, a typical sample size to train a supervised hallucination detector is about few thousands, because you need to somehow collect this data. And typically, it's, okay, for modern LLMs, it's not an easy task to find examples where this model hallucinate, and so on and on. And it means that in this case, we are solving not only the problem of finding some interesting features and understanding better what is going on inside an LLM, but also we reduce the number of features that we input into this linear classifier, and because of this, we can work better. Okay, can we go even deeper into internal states of LLM? Yes, we can. And one example of doing this, again, we have this attention map, but we can look at it as a graph. And basically, we have all the edges here, but these edges are weighted. And the weight at this edge is the attention score between this token and this token here we have. Okay, because it's kind of lower diagonal matrix, we just symmetrize it by reflecting this to the top. And now we have, and also we have kind of different scores here and, okay, and here. But anyway, we do this preprocessing, and we have an edge weight on the strengths of the attention between these two tokens. And so what we can do many nice things with graphs. And also we can pay attention that we have actually tokens from prompt and tokens from response. So we can calculate how connected the prompt is to the response using this attention graph. And one way to do this is to construct so-called minimum spanning tree between prompt and response. So we try to construct the vector that connects all the nodes. Okay, not vector, no, sorry, tree that connects all the nodes and has the minimum length with respect to all possible trees. Okay, we have some things that I kind of skipped because in this approach we also glue all these prompt tokens into the one token and say that the strength of attention between this meta token and tokens of the response is, I suppose it's maximum or maximum of the attention scores. But anyway, we construct this minimum spanning tree and use it as a score. It also has some nice topological interpretation. Specifically, it is mtopdiff score presented in this paper at NeurIPS 2021. And so we can say that we topologically understand what is going on in the representation space and how prompt and response are separated. Actually, we tried to use different distances, and so something like a Euclidean distance between embeddings, it does not work at all. Okay, it works pretty poorly. But if you consider something like so-called kind of maximum discrepancy between prompt and response, also a variant of not a distance, but kind of that calls a measure of discrepancy between prompt and response, it works well. But also we have, and also you can see that it is a single score for single head. So we select head, we have representations here and here, and calculate everything, and we have a single number. So basically we can as much number as we have heads, and also we can select heads. And actually what is interesting is the same head are responsible for hallucinations in different data sets. So there are kind of, let us look at this plot. What does it mean? It means that each dot here is a head, and for one axis, we compute the average difference between score for hallucinated and non-hallucinated examples. Here one data set, here another data set, and we see that for these heads, we have a large difference between hallucinated and non-hallucinated examples. And for all of the heads, it's something around 0. And also we can see, okay, there's the same head here. Yeah, these high scores here and here for MC Marco and COCA data sets. It means that we can select these universal heads that describe that a hallucination will appear. And we can select this head kind of in training-free way, just the head with the high scores if you have about 50 examples of labels with hallucination or non-hallucination labels. Also, we can try, okay, no, we don't have it, but I would say that these heads are not random heads. They actually pretty much correlated, okay, yes, we have this plot, with other type of heads that come from mechanistic interpretability. Basically, people were thinking about what different job different heads conduct. And one of the job is just copying text from prompt to response. They are called induction or copying heads. And okay, we can do this artificially. Yes, we can just generate a prompt and ask a model to copy from prompt to response and see what heads activate most. So we select these heads and we see what is the ranks of these heads in our ranking, what are the useful hallucination detection. And we see that for two different models like Mistral and Llama, the rank of this head in terms of how they are copying, how good they are at copying and how they are involved in the copying is very high. It means that we can do this thing in a purely unsupervised way. So we just select heads that are copying heads, compute with them these distance scores, specifically mTop-diff score based on minimum spanning forest, and it would be a nice hallucination detection score. It's pretty easy to compute in terms of compute, and it also transfers pretty good because of this pretty robust and natural head selection procedure. But actually, we can go even deeper. There are many things that we can look at when we are talking about interpretability, and specifically mechanistic interpretability. And actually, I hope you are now familiar, or you're familiar with induction heads that try to copy from prompt to response. Also, there are other so-called entropy neurons in an LLM. And what they are trying to do, they try to normalize the entropy to make actually the model more calibrated. And actually, what we discovered, it was a surprise for us, is that, okay, from one thing we can see these induction heads. If they fail to copy something, and we have low activation of this induction heads, specifically so-called attention sinks for these induction heads, it means that we have a hallucination. But also, we see that if we have this induction heads, and we go this way through entropy neurons, these entropy neurons make entropy for, if we don't have this copying behavior, make entropy lower. So basically, it says that we are more confident than we would expect. Or in other way, if we copy everything, then we activate this entropy neurons and entropy is high. So we don't know why this happened for now. Okay, maybe we can provide a hypothesis. But it means that we have two conflicting mechanisms. One, and both appear because of induction heads. Because they are responsible for mitigating hallucinations, and also they activate these entropy neurons that make model not very well calibrated. So we made some experiments to look at what is going on and can we confirm this statement with some evidence. And yes, we can say that if we have attention sinks in these heads, it means that we have this high probability to have hallucination. We can compare this so-called sync rate score here. Also, we can see what is going on with these induction heads when we deactivate them during inference. If you're doing this, then we see that loss increases. If you do this with some random heads, the effect is less severe. It means that these are very important heads, and they're responsible for producing hallucinations. Also, we can try to find some correlation between induction heads and entropy neurons. And yes, it is here presented. And also, we can see that, separately, just to double check that entropy neurons, they do correlate with final entropy values. So we can try to produce two scores. One score is based on these entropy heads and how they activated. Another one based on entropy neurons, Another one based on induction heads that we actually developed previously. It's actually a simpler variant of this topological score. And because of this, we can deal with hallucination, and combining these two training-free scores, we can produce even better hallucination detection. And this is because we understand deeper what is going on inside a big LLM. And I hope it motivates you to do more of this type of research. Also, we can look at other papers. They also note some patterns of what is going on inside a big LLM. Again, we can look at this sync scores. Okay, and let me finally introduce what is this sync. We can compute the attention scores between one token and all other tokens. It means how this token affects every other token. And sync means that this token is grabbing too much attention, like it affects everything else. And typically this behavior leads to hallucination as noted in previous paper. And typically it means that this token that grabs most of the attention is some specific token, like it is not a token that model actually should attend to. It is token like beginning of sequence, or it is some comma or dot, so something non-meaningful in the end. And basically we can interpret it as model does not know where to look. And when we see this, we say, okay, model does not know, so with high probability it will hallucinate. We can get this top sync rate scores, like they sorted in this paper, kind of take top k, concatenate to produce some features. And now they have this hallucination probe, again this small model on top of generated features, that produces pretty high hallucination scores. This sync rates, independently verified, kind of somehow related to this. Can we interpret in this way another work, like you have seen this picture before today, and it is about another pattern in the attention map that we can try to identify. So this is again the number of some head, x-axis. Y-axis, it is token in our answer by a model. So we have green tokens, it means no hallucination, and red tokens, it means hallucination. Also, we can compute attention not like to the first token, to some sync. We can compute just attention to the previous token and see how big this attention is. And let us look, for example, at this head. So here is the score, and we see that typically the attention to the previous token is pretty high. But if we have this hallucinated tokens, the attention is pretty low, and it again can be used as a hallucination detection score. Also, we can interpret this, and a good question to ask here, does it somehow connected to attention sync? Because if you have hallucination token, typically most of the attention goes to some kind of nonsense token. And it means that, okay, we definitely will get less attention to the true token. So again, we can see that these strange attention patterns, and we can even interpret them in some way, can help us to say something about the probability of hallucination. Also, we can ask a slightly different question about hallucination detection. So we now see that internal states is something we should explore. And actually, there are other works we can try to do, because mechanistic interpretability kind of is a hot and large topic here. For example, we have this sparse autoencoders to produce meaningful vectors, meaningful representations inside our model, and maybe this also can help hallucinations. And also, again, we have this pretty complex problem on what features should we select, because there are so many of them, and you can see each paper has at least one other feature. And typically not one, but the number of has features, and we still should somehow be able to combine them. So maybe we can try something different. In this case, we are talking about making another model to detect that we have a hallucination. So what does it mean? It means that we have some big black box model. It also hallucinates. And we want to construct a model on top of this to detect if we have a hallucination. And we hope that this model can help us to understand what's going on. Also, there is a fundamental question here. Because basically we consider two different problems. One problem is a problem of generation of some truthful, reasonable text. Another problem is detecting that something is wrong with the generated text. In mathematics, you know that in many problems, creating a solution is a much more complex problem than verifying it. And we hope that something like this would happen in natural language. And we can try to do something like testing on how good can be detectors for detecting like something with large models. And really we can see that this is the case. For example, we can take for generation Llama, Simbi, Mistral 7B, or even GPT 3.5. And as a detector, we use something like very small, yes, the Berta FS3, yes, process less than 1 billion parameters. And really, we can say that even for GPT 3.5, the Rockow score for hallucination detection by de Berta for the hallucinations of GPT is okay, significantly higher than 0.5. It means kind of that really we can do this, and kind of it's not like some strange problem, ill-posed problem. It really is a problem we should and can solve. Okay, I try also to make some kind of summary and say that we have different methods we consider it for hallucination detection, and we can judge them in terms of detection cost and detection quality. And I would say that maybe consistent-based is something kind of in top of quality, but detection cost is pretty high. But when we're talking about something more efficient, it would be something like based on props, like on some features extracted from a model, or these mechanistical features that can do even better with typical additional cost, because we can calculate them on the fly when we are running the model. And maybe a good question to ask is, why do we need this thing? Why we construct hallucination detectors? Okay, it's a nice thing to have. We can say, okay, you guy, you make a lot of errors. Yes, okay. Typically, kind of, it's a great pleasure to do this. But how can we kind of transfer this to specific applications? And let us look through some list I kind of constructed based on what I kind of witnessed. The first thing is a different version of abstaining from answer. And actually, we can do this even before the generation of the output. So we have some input, some question, some prompt, and maybe some context. And we ask another LLM or detector, would this original big LLM answer this question correctly? And if it is not, we can just abstain, and we can save a lot of resources in this way. Okay, in a way, maybe you can connect this to, for example, speculative decoding. Also, if you have this course, we can also like run 5 models and select the best response based on how uncertain we are about this. Another thing and another big area actually is adaptive RAG. So for RAG, how it happens? We have some question, and we have some big database to select relevant sources. It can be internet, or it can be internal database with some documents. And we compute some similarities between the prompt and the document, so kind of some specific vectors related to the document, and extract the most relevant with the highest similarity. Is it kind of, and it happens typically kind of we extract some limited number of documents, so we extract one document. Also, we can do something in between. We can extract document adaptively. We check, do we have enough information about after extracting of this specific document or not? If the answer is not, we are not that confident about the answer, we can extract another document. And we can continue in this way, and in the end, save resources because we extract only when we need, and also have higher coverage of the information, and we hope that the results of the generation would also be better. Also, there are some kind of papers, for example, like better selection of beams in beam search, also a paper produced by Artyom. And also the last thing is a variant of active learning based on uncertainty. Because we try to select some examples in a few short learning regime, or it can be just selection of document for labeling. And after that, if we have this sync, this uncertainty estimation, we can do active learning as we promised before. Also, kind of maybe we can think about it as some general sync. And this is actually kind of not an experimental paper, but a position paper. It says that we should go from uncertainty at specific LLM, specific agents, but rather equip each of them with separate uncertainty estimation head. And if we have this, we can also account for uncertainty about our final decision. So we move from uncertainty at overall, like from entropy, yes, some confidence in some specific thing in generation of tokens, to uncertainty about the decision we should make. Is our code good enough to push it to production? Have we resolved this issue with some kind of during multi-agent discussion? And so on. So maybe we can try to make it more general. And again, kind of right now, kind of 2026, we talk less about LLM, maybe slightly, and more about agents. So basically, we need to think about uncertainty at the level of agents because we have so many of them, hundreds of them now. And also to make maybe kind of use of this hallucination detection and uncertainty sync, I would like to talk about how can we mitigate them. And actually, there is also a very big topic, and you can see that a lot of papers deal with this. So I would like to focus on something I am aware of. Sorry again for mentioning my own papers, but I suppose I understand them better than others, so kind of maybe the talk would be more interesting. So we are considering specific problem for small model to be good at something. One motivation would be to put some small domain expert on your phone. So you don't need an internet, you have a small LLM that runs inside your phone and can handle some simple queries or can handle like not answers, but rather like call specific tools inside your phone. And typical size of this model we can allow to put on your phone is up to like 7B or even 1B. It means that we have a small model, and this model definitely can't memorize all things we want a good model to memorize. But it can be domain expert. We can, in a cheaper way, get good results. And because we have a very big LLM, we can distill it to make everything work good inside it. So we basically have small LLM model, and we distill some knowledge from big LLM. If we are doing this kind of in vanilla way, it's a pretty cumbersome process. It requires a lot of resources and a lot of data for training. And one way to think about this is to look at specific domains. When we have subdomains of this domain, we want the student, like small LLM, to learn. We can find out how bad this specific student model is at this domain and do this distillation with a focus on this domain. So we evaluate training data. We sample specific important parts of information to our batch we are using for training this small model. And because of this, we can significantly improve this sync without kind of losing much of what we want to do. Basically, they propose a specific way to do this, like DDK. And there is regional student perplexity. We want to make it smaller. And plus DDK, we see, okay, in almost all domains, like in mathematics, in Chinese books, okay, well, whatever we have improvement, okay, for almost all domains, we have improvement over what we have. Also interesting that sometimes we can be even better than a teacher here, okay. Maybe because we input specific training data for this small model to learn. Also, we can improve it even further, not like domain level weighting, but specific data level weighting. And what we are doing? We have data that we can use to train our model. We estimate how uncertain is our LLM for each of this piece of data. For example, we can measure the entropy for our predictions for our tokens that we generate, okay, or perplexity for our data. And so now we can split all the data to 3 subparts, so-called easy data, medium complexity data, and hard data. And to distill from a big model, the baseline approach is like this. We reason about this data using large model and learn with our SFT procedure, small model, using the original data plus reasoning. And what we can do better, we can say that we don't need SFT plus reasoning for all the data. We need SFT for easy data and medium data. And for hard data, we would have this SFT plus reasoning from a big model. It means that we spend these reasoning tokens only for a big model. And it means that we can end up using like 2 or 3 times smaller amount of tokens to do this. And actually, it's about very specific application of our third estimation. So we obtained a third estimation for our data, some entropy, for example, or cross entropy, or whatever. And using this, we rank it, we sorted our data with respect to this uncertainty, and pay different attention to different data. And because of this, we made it work much faster. In some experiments, we got even better quality, but I wouldn't say that we are very confident about this. So, to the conclusions. We can do a lot with LLMs. They hallucinate, but we can predict them. And there are many methods, again, it's a big field now, a very hot topic to deal with this. But I would say that it can be pretty easy to do with multiple runs and measuring how correlated, how semantically similar are different generations by same model. Typically better, but typically very expensive. If we are talking about internal states, we can do it on the fly in parallel to a generation of a big LLM, and it works also pretty good, I would say. One example of features that can be used to extract some information about internal state of an LLM are topological features, but in general, I would say that it is about attention patterns and interaction of different elements in our big LLM, for example, induction heads and entropy neurons. If we have the third estimation, we can go further and apply it in many ways. One example being adaptive RAG or abstention from given answers. I thank all people who helped me to prepare this presentation. They were really nice and all errors are mine, but all nice things. And specifically, these papers we published this year are on them. And thank you for listening. And now it's time for questions, I think.
Okay, yeah. Now I'm audible. Thanks for your talk. That's an interesting topic that, based on the internal understanding of the model itself, it's sometimes possible to understand whether there are some hallucinations. And it looks like it's a partial case of just the personality of the model. If the model understands that something is wrong, if the model just honestly tells that is the case, or tries to cover it up. And in that case, maybe we should use typical ways to tune or analyze personality of the model to work with hallucinations too. First, maybe if you're speaking about that different heads may know or are responsible for hallucinations, then maybe we should use this idea and recollect that sparse autoencoders are also trying to separate different activations or different heads, different internal representations, and maybe some of the autoencoder activations are responsible for such hallucinations. And maybe you can use steering based on that, and maybe also just everything can be solved by the right SFT or alignment.
Okay, I don't hear a lot of questions here, but mostly statements, but I will try to address them. Okay, so basically, yes, there are some works that trying to mitigate hallucinations, and one way is SFT. SFT is, okay, something I suppose most of you would not know because, like, especially for large models like 30B models, you can't afford SFT. Maybe some steering would work, but still kind of is questionable about efficiency of the current steering, and really it works to some extent, and we see some works that try to apply kind of a way of steering on top of the scores and help to do this. For CE, I wouldn't say kind of it tries this, but the result was not that inspiring, but maybe kind of someone else can do better.
Okay, and concerning the usage of attention scores, first, is it indeed correct to say that if a model attends at least in certain times to the tokens that are recently generated, there is definitely a hallucination, or maybe it's contextual and the heads understand that this is not the time to look at my response, but it's time to look somewhere else. And actually, attention scores, good ways to measure if those tokens are responsible for generating these tokens. Maybe we can use integrated gradients or some other methods to determine it.
Okay, a good example to answer this is large vision language models. In this case, you have some question, you have some image, and you want to, for example, describe what's going on in this picture, maybe reason about this. And the thing is that mostly, almost all modern models have this not very desirable behavior. They try to forget about this image and focus more on context and on some internal load. So basically, we can describe it, okay, that it forgets about another modality, and we can try to apply gating to make it kind of more grounded on this image. And also, we can try kind of about detection to see how attention works and fixes in some way. Also, I would say that anyway, it's maybe kind of very natural behavior for an LLM, even if it if it does not have the context. We have a question, and it is a very important piece of context. Yes. So basically, we need to attend to kind of specific words in the question, not to beginning of the sequence.
Thank you so much for the presentation. I have more of a maybe philosophical question about hallucination. So, to me, if we think of this as a way to estimate the distribution over text, essentially this idea of hallucination is that, there is an intrinsic problem with the fact that these methods are probabilistic in a way. So we're estimating, we're generating from a distribution, and then when we obtain samples from the tails, we may not like them because they are plausible under the model that we constructed, but they are sort of at the edge of reality according to the data set that we have. So by mitigating the effect of the hallucination, we're essentially, my understanding is that we're avoiding the model to sample from the tails of the distribution, and we're encouraging the model to stick to a region where things are most plausible, which is sort of focusing on the central part of the distribution, if you like. And is this, is there not like a trade-off that is maybe impossible to solve? We would like the model to generate things that are as diverse as possible, but at the same time, if we do that, we incur into hallucination. So we want to mitigate this effect, but by doing that, we reduce diversity. So is this trade-off ever possible to resolve? And I mean, when these approaches apply these mitigation effects, is it possible also to measure how much we lose in terms of diversity of the samples, if that makes sense?
I would say that, okay, I would split the answer to two parts. The first thing is that when we train the model, we are very strict. Like we have only one correct, okay, we train it with typical next token prediction task, and we have only one right answer. So it's very natural for a model to be overconfident because it is trained to have only one option in the output. We have some fundamental flaw. We don't know how to fix this because we will not be able to mine enough training data that provide diverse answers. And okay, that's one problem. That okay, philosophical problem on how we should train them and how we can, more practical perspective, how we should improve this process and is it possible anyway. And for the second question, I suppose, and kind of there are some other teams in the world that are working on this, that we should kind of have many types of hallucination and uncertainty related. We should focus on different types, and we can say that okay, this diversity is okay. Kind of we change word by a synonym, nothing happens, it's okay. It's still a good answer. So we should stay with it, and we should keep this diversity in the generation. Maybe at some higher level, like to produce some diverse results. Maybe kind of person is asking like for 5 tips to improve his productivity, and we should be, I suppose, as diverse as possible. And also, for some things, I suppose we should be very strict. For example, we should not produce something that contradict the context provided by the model. Basically, there is approaches of thinking that, okay, we have many sources and some sources are less reliable, some sources are more reliable. But in general, we should kind of listen to what we have in our prompt and believe in this. And this would be kind of, should be prohibited at least. The probability should be very low to generate something that contradicts. We disintegrate this part of uncertainty about like how much fantasy do we have, how much diversity do we have, and that things that the rules we should not violate.
Thank you. This is very interesting. Thanks.